Did you have a chance to look at that video I sent?
Yes, I did. I did watch the video. The one of a set of rare earth magnets being spun around the screwdriver and traveling up, I'll say loosely.
Right. Well, not loosely. It's always up, right? Like that's the one thing that's constant.
I guess up with respect to what it was if it was respect to the screwdriver. I mean, if you watch the video, you find out it's with respect to the earth.
Yeah. So let me just say to begin, I have no idea how this works, and I've thought about it a lot. And I've watched the video like 3 or 4 times, and I have no clue. I have one thing to say about it, and then hopefully that'll take us somewhere. But I definitely didn't watch the solution. Hopefully you didn't either. But
I didn't. I stopped it at like 2, right as he started to say something. I was like, oh, I'm at the time. Pause.
Yep. Yeah. So yeah, this is a Veritasium video, which is actually done by someone else named Steve Mould, who I've seen before, but I don't know his channel on YouTube at all.
I've definitely seen videos with him. Yeah.
Yeah. So the original puzzle was a stack of magnets, like little disc magnets, maybe a couple inches long, stuck to a screwdriver. And you swing the screwdriver around, making like a circle with the tip of the screwdriver. And the magnets spin around the screwdriver like you think, but then they also go towards the tip. They always move up. And it doesn't matter, like he did it, the guy in the video did it with the tip of the screwdriver down and spun the magnets around the screwdriver, and the magnets also went up, so away from the tip in that instance, which was kind of strange. So he was saying it's not just like centrifugal motion, like flinging it towards the tip, the bigger circle. It's something else.
Right. Which is definitely what I would have thought.
Right. That was my first thought. And then he's like, no, it's not that. I can read your mind. And that is not what it is.
Yeah. And then you can do it left ways or right ways, spin it, counterclockwise or clockwise. And it doesn't matter. That doesn't affect it either. It still goes up. And up is, with respect to the ground, it's going
exactly
up.
Right. And then the craziest thing of all that I was not expecting, and that made me think a lot, was his demo of, like, he attached the screwdriver to a drill and just held it completely vertical and turned on the drill, it looked like, and the screwdriver spun around really fast with the magnets spinning and moving up. But then he put a ruler to stop the magnets from going around the screwdriver, but the screwdriver kept spinning. And the ruler just basically acted as a way to stop the magnets from going around in a circle, but they still climb the screwdriver. So screwdriver spinning in place and magnets just climbing up with the ruler blocking them from spinning around the screwdriver. You got to watch the video if you haven't seen it yet. Click on the link and stop at about 2 minutes because that's when he starts explaining things.
Yeah, I mean, I feel like that test was really great because the putting it in a drill makes everything spin concentrically. So you don't have, like, when you spin it by hand, you kind of like sweep out a cone and to some degree. But yeah, when he puts it in the drill, now it's just rotating about an axis. So he's essentially eliminating 100% that idea that you're flinging it out like kind of towards the edge, I think.
Right.
Yeah, but then he put the ruler there, and it just, that to me as well, I was like, okay, now I'm really confused. Right.
Like I had some inklings of ideas of maybe how this worked, and then that just threw all of them out the window. It's like, okay, I actually have no idea how this works. Now it's like, we need to go into Maxwell's equations.
Yeah, I definitely think there is some, moving magnetic field, changing magnetic field sort of thing that's happening here.
Yeah.
But the one thing I feel like we can say fairly confidently is that it's got to be related to gravity.
Exactly. Yeah, that's the only thing symmetry-wise that's broken in every demonstration they showed, is that there's a force of gravity down on the magnets.
Yeah, that's the only constant between it all. So it's like, okay, so somehow gravity is involved, and somehow I feel like there's got to be like a electromotive force type of, current loop thing that I haven't figured out, or I'm not sure. I
haven't gotten that far into thinking, but I mean, yeah, my hunch is it's something like that. But my first thought, and I still haven't, this hasn't been ruled out for me based on what I've seen. The little bar is being pulled down by gravity.
Sure.
And it's being pulled down in a way that kind of breaks it off of the screwdriver. Like it wants to break off of the screwdriver.
Right.
So imagine the bar attached to the vertical screwdriver. The bar is horizontal. It feels a little torque that wants to pull. If you imagine the last magnet that's stuck to the screwdriver in contact with the screwdriver, imagine that little disc as it's attached to the screwdriver breaking away, with the top pulling away but the bottom staying in contact. So there's like a little wedge of like a little magnetic field gradient right there. I feel like that's the key.
Sorry,
I don't know what it...
Say that one more time.
The flat part of the magnet, the magnetic discs, it's in contact with the screwdriver.
Right.
And it wants to break away by the top pulling away from the screwdriver, but the bottom stays in contact.
Oh, okay. I see what you're saying. Okay.
It wants to make a little air gap, like a little wedge where the magnet's not in contact at the top, but it's still in contact at the bottom.
Right. Gotcha.
That's the only thing I can think of that would cause any sort of change. Like what would gravity be doing here? It's like something with it, like pulling away from the top, but still being connected at the bottom.
Right. Yeah. I mean, like we know gravity can like hold things up. That's not the right way to put that, I feel like, but like we get weird things when like you have the spinning wheel demonstration that everyone who's taken, mechanics class has seen, where you spin the bicycle wheel up really fast, or well, you don't spin it first. You just hang it by a string on one end and you let go and it just falls down. And you're like, okay, that was boring. And then you spin it up really fast. And now when you release it, it doesn't fall down. It wants to process.
Right.
So I'm not saying that's what's happening here, but it seems like, yeah, there's got to be like some interaction with gravity and something else somewhere. And it seems like, okay, maybe there are some spinning things. Maybe something like this could, I didn't know exactly what. It's not spinning the same way that the bicycle wheel is spinning. But yeah, then as soon as that ruler hits and the magnets stop spinning, but the screwdriver keeps spinning, then all bets are off there. So yeah, the only thing I can think of is sure, I can follow you down this path where we have the little air gap being formed.
Right. So maybe a way to think about this, what would you change? Like what would you test? Like what would you, if you had your hands on this and had whatever equipment you needed, like what kind of tests would you run to try and figure out how this works?
Well, the first thing I'd do, just out of curiosity, is I would try less magnets. I would try because it's a stack of little disc magnets. I would try taking some of them off and seeing if this effect still happens. Because I imagine when you have one little tiny disc magnet attached to it, that this doesn't happen.
You think it wouldn't happen?
At least like not in the appreciable way that it does in the video. So like maybe it would happen, but on a much larger time scale that it would take for it to climb or something.
What if you replaced all the magnets except the one closest to the screwdriver with something that's not a magnet but still the same mass, like attached I don't know, a piece of lead, or like a
super glued non-magnetic material to it.
Mm-hmm. Yeah, that's in the same shape, like it's a bar shape, but it sticks off the screwdriver. Would it still happen?
I would think so. I think in that case so that too. Would.
I think so too. Maybe not as strong. like it's like the strength of the permanent magnet that's attached to the screwdriver makes it more dramatic. Maybe it rises more quickly. I don't know, but we don't have to worry about that. But yeah. So that to me, bringing gravity into this, that means that like the amount of torque causes this to happen more dramatically. Like that would be a test of that.
Yeah.
Like, how much does this magnet want to fall away from the screwdriver?
Yeah, or try adding more and more magnets and see how that's going to change it.
Right. I was thinking, what if we added, like somehow attached, basically got a duplicate of that stick of magnets and put them on the other side, exactly in the opposite side of the screwdriver, and somehow attach them to each other. So like the left side is holding up the right side. Does that make sense? So that there's no torque, but there's still bars of magnets there.
Okay, so are you
I'm trying to think of a way to...
Are you saying like we build like a little cross instead of a T?
Yeah, exactly. Like somehow get the magnets on either side of the screwdriver.
So they're 180 degrees apart. That's what you're saying. Okay.
Exactly. And somehow supported, like I imagine something like the shape of like a a nose, like a I don't know what they're called. Those little clamps you put in your nose to like plug your nose when you're swimming or something like that.
Yeah, like, or what if we took a washer or something and like a key ring and super glued a string to the end of the magnets, the end not touching the screwdriver, and then put the key ring around at the top of the screwdriver. And so, the tension in the string would be what's holding it up, but it's still free to spin.
Right. Exactly. Yeah. Somehow it supports itself. So there's like, if one side wanted to tip, it would pull up the other side. Like if one side wanted to fall down, the other side would get pulled up and vice versa.
Yeah.
I don't really know what I'm thinking, but
I'm following. I think these are all good tests to help us narrow it down. Go ahead.
Yeah. I have one final test though. So that's one idea to check like how gravity is affecting this. Like if we hold it up, does it stop doing this? The other one is it something to do with the screwdriver being round? And if not, what if we had like a sheet of metal that was made out of the screwdriver material? Like instead of a cylinder, it was a sheet. And we ran, like the sheet somehow moved quickly past the magnets. Would the magnets climb up the sheet as the sheet moved past it?
Right. I see what you're saying. Yeah, I think that's also an excellent test. Much harder, I feel like, to do. But it's also an application of the same idea.
Like if we put the magnet between two books or two flat things, supported them left or right, and then the screwdriver, instead of the screwdriver, it's like a wall of metal, and we just slid the books across the wall of metal, would the magnets start to rise up? Or maybe we don't even need the books. Like I'm trying to think of somewhere to let them be free to move vertically, but constrain them horizontally to move to the left or to the right. Like would they go up? Is
there I could think of a way to do this. Mm-hmm. If we had like a essentially like the he puts a ruler on there, right?
Right.
So just have a corner where, one part of the corner that the magnet is not attached to is a non-magnetic material, and then a sheet that is a magnetic material, and then you just pull the sheet so it pulls the magnet into the corner against the non-magnetic material. Would it rise? Does that make sense?
Yeah. Yeah, and it's still tripping me out that there's like gravity is the thing that plays a part. Like if we put the sheet like as the floor in the room and move them sideways, it wouldn't do this. I don't think.
Yeah, I don't think he ever shows him trying it horizontally, but
based on
what would happen?
The like left versus right spinning, it always went up.
Yeah. What if just another test, what if you put a non-magnetic material in between the magnets and the screwdriver? But, not so thick that the magnets weren't clamped
attached
to it. Yeah.
Right. Yeah. And what if it was wedge shaped? Like I'm thinking it's pushed away slightly on one side versus the other. And then we laid it flat. Like would it work then?
Oh, that's interesting too. Yeah. That would be a great way to test out the wedge theory, having something to do with it. Or, well, I'm kind of wondering, like, what if you broke electrical contact? So like you put, like a little piece of plastic in between. Do you think that would change it? Is there some sort of current that's being generated somewhere?
I don't think so. My gut says no. Maybe there is, but I can't imagine it having that strong of an effect.
Well, I'm imagining like some sort of eddy current.
Yeah.
That would
maybe
do something. Or what if you replace the neodymium magnets with just, iron magnet, like a weaker magnet?
I mean, my guess would be the effect's there, but it's just going to it's not going to be as dramatic.
Yeah, I would think so too.
But the conducting part's kind of interesting. I mean, I think I'm guessing we're going to have, well, actually, I don't know. I was going to say, I'm guessing we're going to have some sort of electrical effect based on the changing magnetic field creating, I don't know.
Yeah, well, in the screwdriver, we're kind of setting up like a spinning magnetic field, right? In either case, like say you take the north end and you attach it to the screwdriver. By the way, the whole time I'm talking about this, I'm thinking of the screwdriver in the drill example.
Okay.
Just, probably for the whole time of this conversation, because I think that's the better
it shows it the best, like what's happening.
Yeah. So yeah, you take the north end and you touch it to the screwdriver. So then the screwdriver is going to generate a south pole at that point of contact, right? Mm-hmm. And then as you're spinning the magnet around, I don't know exactly what this would do, but you're inside of the screwdriver, you're getting a rotating magnet that's going around the screwdriver, like inside of the metal.
Right.
And that's also the case in the reference frame of the screwdriver when you have the screwdriver spinning, but the magnet staying still. So don't know if that has anything to do with it, but
yeah, let's work with the screwdriver and the drill. Magnets in place, you bring it up to the screwdriver, and then you start spinning the screwdriver. So we have north pole touching the screwdriver, making the screwdriver south pole, but then that spins away from it. Well, let's do it without it spinning. If we touched a magnet to the side of a screwdriver, the north pole of a magnet to the side of the screwdriver, the side closest to the magnet would become the south pole. Does that mean the other side of the screwdriver is the north pole?
It should, I would think.
Like, does it permeate all the way through the screwdriver to the other side?
I mean, I think that would depend on the material,
right,
and that sort of thing. But in general, if you talk about with like an iron thing, probably,
yeah. I've touched a magnet to a nail, and then picked up a paper clip on the other side of the magnet. So yeah, okay. So you have a south pole close to the magnet and a north pole on the other side.
Yes.
Then you start it spinning. What happens?
Well, clearly it just climbs up the screwdriver.
Right.
From all of that information. I mean, the thing that I'm seeing is you get in the frame of the screwdriver, you're getting like a rotating magnetic field or spinning magnetic field.
Right.
Now, how that does anything, I'm not sure.
And all the while, like, we can't be working with some sort of like right-hand rule. I mean, I guess we could, but it's always going up. That's the problem. Like, it can't be just
right. It has to be more than just what I've said, the spinning whole thing. There has to somehow gravity has to be involved.
Right. And the way the video made it seem like it wasn't like if you spun around the magnet, it would always go down. Like, everything they showed made it seem like it was always against gravity.
Yeah.
At least that's what he implied with his with the little videos.
Right. And I think that's probably a fair assumption.
Right. I'm saying he didn't withhold something and be like, oh, actually, if we would have showed you this, this is how it works. Like, I think everything points to it going up no matter what.
Right.
So what we just described, how does gravity fit in? Like, it's got to be the torque on that bar of magnets. If it pulls away.
Right.
Let's say it starts getting repelled because all of a sudden there's a north pole facing a north pole.
Okay, like it's spun around and the fields haven't quite flipped yet.
Right.
Okay.
I don't even know if that makes sense. I feel like the polarity would flip faster than the screwdriver could spin around.
I would think so too. Yeah. I mean, that'd be another test. Does the speed matter?
Right. But let's say it did. Let's say we got a north pole coming into another north pole and it's like about to turn into a south pole.
Right.
But it hasn't yet. So it starts to repel. And I think that what I was saying, like the top of the magnet would repel first. What would cause it to go up though? I don't like this path.
Yeah. This might not be the right path. I mean, we can walk the air-gapped wedge path, but I don't know where that runs after we say we accept that there is a slight gap at the top, the upper part of the magnet versus the bottom part.
Also, what bothers me is that it took a lot of people to figure this out, and a lot of people who are smarter than us. And it took them a long time. Like, it passed through many people before someone answered it.
Well, we could always run more tests. I have neodymium magnets, and
you actually have this stuff.
Yeah, not right here, right now, but come next recording session, I could run these tests live.
Nice.
But can we go down the eddy current path? I don't know exactly what that means, but I'm just trying to think. Okay, so like when you take a neodymium magnet and you drop it in air, it accelerates just like any other object with 9.8 meters per second and falls to the ground. But you put it in a copper tube now, and it falls much slower. So what's going on there?
Changing magnetic field produces an electric field in the copper tube that pushes a current, and that current creates a magnetic field that opposes the falling magnet's magnetic field.
Okay, so it must produce then a current around the pipe? Would that make sense?
Yes.
But wouldn't that just want to flip the magnet?
Flip.
Yeah, okay. So let's say you're dropping it north side down.
Uh-huh.
And it's falling through. There's some current that's going to be produced that's going to oppose that change. So like if you dropped it just through a wire loop, the wire loop is going to produce a magnetic field that has a field north side up, right?
Right.
So wouldn't it just want to flip the magnet? Like the magnet, those two, that dipole interaction is going to make it want to flip over, I think. In my intuition. But if you've ever seen the magnet fall down one of these tubes, especially if it's like a big enough tube, it like almost like locks in place.
Yeah, now that I think about it, I've only seen them when the magnet's like almost the same size as the pipe itself. So it like hit the wall and like couldn't flip over. But let's say it was a small magnet like the ones in this video, and the pipe was something a lot larger, like, I don't know, a silver dollar around. Okay. And you drop one of these small magnets, if it flipped, then the pipe just makes the other opposing magnet and slows it down.
Right. But
if it was sideways, then what would happen?
So I think what actually happens, I'm kind of on Wikipedia a little bit here too, but I think what happens is you actually produce, it wouldn't be like a loop of current like around the pipe, but it's like a loop of current in a circle on the axis perpendicular to the pipe, I think is what happens.
If the thing was falling sideways, is that what you're saying?
Or in general, maybe it falls like, okay, maybe if you could drop it perfectly straight, something would happen. Like it would rotate slightly sideways, and once it's slightly sideways, now you're gonna have the other fields being formed.
Okay. The other kind of standard demo for eddy currents is, well, usually it's magnets fixed in place with a gap between them. So there's like a strong field in between two magnets, and then you swing like a pendulum that has like a metal sheet on the end of it, like a copper sheet on the end.
Yes.
And then it'll slow down that pendulum.
Right. And so that, I think, that does produce like a surface current.
Mm-hmm. Yeah, like yeah.
Okay. All right. This kind of shows it a little bit. I'm going to show you, send you a real quick video. We don't have to talk about it, but so it's just, if you skip ahead to like, where was I? 55, or a little bit before 50, maybe like 45, you can see him drop it down. And you see kind of like it almost locks in place.
Yeah. Let me see. Yeah, it like starts to tip and you can hear it hit the side. Although, I mean, I don't know if that's because he just dropped it off center, or if like what you were saying, like it wants to flip over, but then it hits the side and gets stuck. But it definitely doesn't like drag down the side.
Yeah. So I don't know exactly where I was going with that part of it. I want to see to get the effect fully thought out. So so it produces like these surface currents.
Did you go further in the video? Like a minute 17?
No.
Minute 15? So he has a solenoid.
And that doesn't work, I'm guessing.
Mm-hmm.
Right. Okay. So it's got to be it's a current that gets formed on the skin of the copper. Like if you curled your finger in the direction of the current, it's going to be either pointing inwards from the pipe or outwards from the pipe, depending on the direction of the current, but not up and down along the pipe's length. Right?
Yeah. I'm watching ahead. Watch at a minute 40.
Oh, it does. Okay. That one's kind of rotating as it's going.
Yeah. But it's weird. It's like, it kind of is happy to stay sideways for a while, but it's still being slowed down.
Okay.
I'm going to say something. I don't know what it means, but maybe you can make sense of it, or it'll trigger some way of thinking about this. What if we replaced the copper pipe in these eddy current demos with an iron pipe, something that's magnetic and conducting, so that the magnet was attached to the side, So my point is the copper exerts an upward force
right
on the magnet always, right? As it spins, as it flips inside the tube, right? Gravity's pulling it down. The eddy current is causing an upward force always.
Okay.
So what if we eliminated the pulling down motion, like if we prevented it from falling down, but we still kept the pipe moving?
So if we pulled the pipe up?
If you pulled the pipe up, I think the magnet would go up with the pipe. Is that true?
So, well, in some regard, I've done the experiment, I guess, where I take a small pipe, copper pipe with a neodymium magnet inside of it, both resting on a table. And if you pull up really fast on the copper pipe, the magnet will come up with it a little bit and then fall out the end.
It comes up with it.
Yeah.
Okay, that makes sense to me. So what I'm getting at, I thought what I was getting at was that the magnet being attached to the screwdriver eliminates the falling that we're seeing in these demos and only creates the upward force.
I like it. Okay. Yeah. So so copper is not magnetic. So it doesn't want to be, it's not attracted to the sides as it's going down. And an eddy current is something that happens in conductive metal. Like it works with aluminum. That's how roller coaster brakes work. Actually, I don't know if they only use aluminum, but
it doesn't have to be copper, just anything that's conducting.
Yeah. So you're saying combine those two things, the magnetic force will then hold the rod, or hold it to the rod or the pipe or whatever we're talking about. And now somehow the eddy current is going to push it upwards.
Yeah. Why is it always up though? That's what I don't get.
Well, I think it's opposite the motion, at least in the pipe, the falling thing. Is like if you were, Tom Brady or something, and you could throw the magnet upwards through the pipe, I think it would, there'd be a force slowing it down faster than just gravity.
Got it. It's just a drag. It's always a drag, but it's different than drag because in the magnet on the screwdriver thing, it just goes, it's applied. What's it applied against though? There's no, I don't get it. I'm stuck on the screwdriver magnet bit. I follow it with the eddy current in the tube and the magnet falling down the tubes. I get it. And I get the, like, if you throw it hard, it'll be against its motion. But then I'm stuck on the screwdriver. I don't get how that translates to upward force on magnets attached to screwdriver. Like it starts to slip and then the eddy current applies a force upward that's stronger than gravity always.
Yeah. Because let's just say, let's say somehow eddy currents are involved here. That's putting some upward force on this. That's not telling us how gravity is entering the equation still.
Right.
So what is
it like the magnets want to fall down and they like start to slip, but then the eddy currents push them up, and the eddy current. What I don't understand is why is the eddy? It's not like drag. Like drag can't be. What am I trying to say?
No, I think you're right. That I don't think it can be.
I can't accelerate something that's sitting still upward. Well, unless, I don't know.
Right. Well, so I'm thinking like eddy currents, require some motion, but it's always opposed to the, a drag force is always opposed to motion. Mm-hmm. So it seems like if it were an eddy current, once it started moving up, it would be wanting to then move down. Like the eddy current won't be wanting to stop it from going up once it started moving up. Like if it's always going to be opposed to motion.
Mm-hmm. Is it like the magnets attached to the screwdriver? Because let me say it this way: there's always relative motion between the magnets and the screwdriver when this happens.
Right.
Like I have to watch the screwdriver on the drill more carefully, but you never see the magnets and the screwdriver spinning around together. I want to go back to that part. Ooh, I almost just skipped too far ahead. 1 minute 20 is where it happens. Oh, wait, no, that's not it. 1 minute 30, about 1 minute 28 or so is when the drill comes in. Oh, I think I just saw something. At exactly 1 minute 30, it's not, the magnets are not moving up the screwdriver.
Okay. So I'm at 120 right now. So I'm...
Okay. The drill starts at like 128 or something like that.
Okay. So yeah, I see. So it's when he first turns on the drill. So yeah, this is something we both missed. When he first turns on the drill, the magnets are spinning maybe with the drill, like the magnets and the drill are both spinning.
Right.
And it's
together, not
climbing up. Yeah. I think we can assume together, but yeah, it's hard to know for sure. Yeah. And then he stops the
second he stops the magnets with the ruler, but keeps the screwdriver spinning, but the magnets held in place, it starts to climb.
Yeah, so I think we could make the assumption, that they're moving together, and then, so there's no relative motion between the screwdriver and the magnets. They're like a rigid body. And then once you stop the magnets, now we're getting some relative motion, which is now creating some force that is somehow related to gravity that is pushing the magnets up.
It's like it wants to stop. It wants to fall, but this eddy current business is holding it up. Man, I want to turn that screwdriver sideways really bad. So I still don't really get how I can visualize the magnet falling in the pipe, like perfectly north pole pointed down. I get it. There's a current in the pipe that creates another opposing north pole. But I don't really get how when the magnet is sideways, what's happening? Because it still works when the magnet in the pipe is sideways.
So I'm looking at the Wikipedia picture here, and
for eddy current,
yeah. And what it is it's, you imagine, if it's fairly close, the magnet's fairly close to the copper, the surface, then you could just imagine essentially all the fields that are penetrating the copper are within that. The square, if you have a square magnet or circular magnet within that cross-sectional area of that magnet.
Okay.
So as the surface moves, or as the magnet moves across the surface, in the part ahead of the magnet, you are now putting B fields that are there that didn't used to be there, that are penetrating the magnet. So it creates a current counter to counter that magnetic field that you're adding. At the other end of that face of the magnet, the same face, same north end or whatever, magnetic field is leaving the cross-sectional area. So now you're creating a current that's going to add magnetic field back. So you actually are generating two magnetic fields with an eddy current.
That are in opposing directions.
Yes.
I think I'm looking at the same picture you are. The one with a sheet of metal pulled with the velocity v to the right, and there's a north pole above the sheet, and to the right, the eddy current is creating additional north poles because the sheet is losing north pole flux.
Right.
And then to the left, there's a south pole, but the sheet's being dragged. So my question is, what force is on the magnet if that's happening? I think it's going to be pushed to the left. Is that true? Because to the left, there's a south pole. No, there's not. I'm sorry. I'm saying this completely backwards. Do you know what picture I'm looking at?
Yeah. I'm looking at the one with the wobbly metal labeled C going V to the right.
Right. Exactly. So a sheet moving V to the right. There's a north pole above it. Look at the blue arrow closest to the direction that the sheet's being moved, like
on the right
side. It points down,
right,
which is the same as the north pole magnet above the sheet.
Right. Yeah. Because the magnet has the north pole down. The head of the arrows then are down.
Right. But that is a north pole starting at the sheet pointing down, which means it's kind of like a south pole above the sheet.
Right. Okay. Yeah.
So look at those current loops. Yeah. Basically, the south pole of those current loops that make that downward pointing magnetic field. Mm-hmm. Above that loop of current is a south pole, which the north pole would be attracted to.
Right.
I don't really know where this is going, but I wanted to at least talk through which way this magnet's going to be attracted.
Right. Yeah. So
and it's going to be repelled by the up pointing magnetic field to the left of the north pole.
Yeah, so it seems like this magnet would want to move to the right.
The sheet's moving to the right. The magnet wants to go with it. Which is what you said. If you had the pipe around the magnet and pulled the pipe up, the magnet wants to go with it.
Right.
I mean, it's a complicated way of just saying if something changes, nature wants it to not change, and it'll try and keep things where they are. But why does the bar of magnets go up the screwdriver if you spin it? I'm losing that connection every time I get there.
Right. So I think one of the things here is take this sheet that we're looking at and curve it away from us and in a circle.
Okay.
And connect it to the other end.
It's kind of like we have a magnet on the outside of the pipe. That's essentially what we're doing. Is we're putting a magnet on the outside of a pipe.
Right. Everything that we just discussed with these eddy currents just says that it'll move either in the direction or against the direction. But I think it is in the direction of the spin of the.
Yeah, exactly.
Has no up and down component.
Exactly. I'm not seeing where to get an up and down component.
Right. Okay, so maybe this is a rabbit hole.
Oh. Let's I might have it. I don't know yet. So stop all the spinning, stop all the moving, stop everything. All you have is a huge magnet that's like, I want to like really exaggerate this. Say you had a bar magnet that's the size of a coffin.
Okay.
Stuck to a wall. There's like a huge wall.
The one of the smaller surfaces?
Yeah, exactly.
Okay.
Yeah. The smallest surface of the coffin is where the bar magnet's north pole is, and it's attached to a big iron building.
Okay.
So you're holding up, or this coffin of magnet is held up, attached to that. Then let's say you push down on it, try to separate it from the building. I'm getting to that little wedge thing.
Right.
So all of a sudden you're removing north. Basically, you want to pull it down. You're removing north magnetic field.
Okay.
From the top part of the magnet where it's attached to the building.
Okay.
So the building wants to make up for that. So it makes more north magnetic field flux at that point, pointing into the building. That means on the outside of the building, the little currents that you set up by removing the magnet right there is a south pole point.
Right. So it's attracting.
So it's gonna try and attract. Yeah, it's gonna try and suck the coffin back up towards the building. But why does it make the coffin go up?
No, yeah. No, I mean that makes total sense because it. Okay. No. Okay. All right. Well, yeah. Why does it not?
Why doesn't it just stay where it is? Why does it move up?
Yeah. Why does it not just go back to being flush with the building?
Exactly. Or maybe that's it. Maybe it's the same reason we're saying that sheet that's being pulled underneath the magnet attracts the magnet to the right, the direction of motion. Well,
sorry, I found a rare earth magnet on my desk, and I wanted to see if I could get this to kind of happen a little bit. Maybe we could learn something, but it's only a single magnet, and I can't get it to spin independently of the.
It attaches too strongly.
Yeah. But
I think it's that torque. It's that pulling away motion.
But interesting to note is if you put it on, so it's a disc magnet. If I put it on sideways, so the edge of the disc is attached, so the north and south pole are facing up and down. It doesn't go anywhere.
Oh, you can roll it around that way, and it doesn't do anything.
Yeah.
Right.
I'm kind of liking this thought process that you were going through, where if you pull it away, that's the only thing so far that's giving us an up force.
Right.
But clearly, make it stop spinning. Like, so the nothing is spinning yet, and you displace it a little bit from being flush. So you create a little bit of a wedge. I feel like that is going to make some sort of oscillator. Like it'll go back and hit. Gravity will want to pull it back down. It'll open back up, come back. I feel like that would just make it the gravity pulls it down. Like let's say not even like you pull it down. You're just holding it up so it's flush. Then you release. Gravity pulls it down a little bit, creates a wedge. You get the south pole. That pulls it back up. Then gravity pulls it back down. And once it's done, the pole's gone. And I feel like it would just like go in a circle there. Also, this just occurred to me. I have two quick comments. One is there's already a south pole if it's a magnetic material, right? Like the second it's touching it, does it get more of a south pole if you pull it away?
I think
it just tries to keep like the same.
Oh, yeah. So, yeah, we're forgetting the fact that the screwdriver is magnetic.
Yeah.
Basically, I was talking just straight. Well, no, I had to be sticking to an iron door or like an iron building or something like that. It wouldn't, basically my coffin experiment, it wouldn't be held up with a copper building.
Right.
It has to start attached to the side of something. But to answer your question, yeah, I think it does just get more south.
Because of so like I'm imagining there'd be two effects happening. One is you're going to get less of a south pole because the magnetic field is further away, and so the alignment is going to be less.
With a wedge in there, is that what you're saying?
Yeah. When you start making the wedge, you're since you're pulling it away, the magnetization part of it, not looking at eddy currents or anything, is going to make less south poles because the objects are further away. Therefore, it's easier for them to like move out of alignment somehow. But opposite to that is, the eddy current that would form is going to increase the south poles there.
Right.
So I don't know what the net is, if it's a gain, a loss, or neutral. But it could be. I feel like it could be either one of those, any of those three things. Okay. The other thing I had to say that I was thinking about is there any way that friction is involved? Because objects have higher, like the coefficient for static friction is higher than kinetic friction, right?
At some point that entered my head. I didn't say it, and I don't remember what context it was, but the static versus kinetic friction definitely popped in my head at some point. Like, oh, are we comparing those two things? And it's like static isn't strong enough, or static is too strong, but kinetic is not strong enough, so it's overpowered. Yeah,
like I don't think this is quite right, but maybe the context was when it's, when he has the drill or the magnets attached to the screwdriver and the drill without the ruler, it's spinning together. Nothing's happening. It's just spinning. But then he stops it. Okay, now we have kinetic friction between the two surfaces. Although the friction isn't up or down, it's left and right. It's in the direction of motion, so I don't know if that matters. But then maybe if somehow it becomes loose, it'll want to move down. And if it's moving down, it can create an eddy current that might push it up. But I don't think that's right. Yeah, the only thing I've seen that we've said that seems like anywhere near like a generate an upward force is pulling it away from the edge will induce an eddy current that will want it to move up, or at least attract the part that has been pulled away back to the surface.
Right.
Could that?
I just feel like that's not strong enough. Like that wouldn't be strong enough.
Could that be it? Maybe is if it's no. I feel like that wouldn't work. But I was thinking like maybe it is like an oscillation thing. Like it gets pulled down, snaps back up, and when it hits, it slides a little bit up.
Right.
And then it slowly pulls back down, and then it snaps back up and hits and slides a little bit up. And then if you do that fast enough, quickly, it looks like it's just going whoop, up the...
Right. Oh, that could be something. I'm watching his replays and listening, trying to hear.
Yeah, there's like a rattling. So you're hearing,
yeah, there is a little rattling. Not every time, though, but maybe I just can't hear it. Especially at a minute 20.
Yeah, that's right.
Minute 17.
Where he's doing the slow-mo.
Yeah, so maybe it's when it falls away, it gets what I was saying. Like you're losing some magnetic field towards the top. So it tries to make up for that, and then it attracts the magnet and kind of pulls it back upward, which snaps it up enough to give it some momentum. I feel like it would be a bigger effect downward, though. No.
Well, so, we were just saying we didn't know if creating an eddy current would create more, less, or equal number of south poles by pulling the magnet away. Well, if we assumed, I'm just making a huge assumption here, that it increased like the strength of the magnetic field, the south poleness, I guess, of that part of the screwdriver, then so maybe as it pulls away, it gets stronger than it was when it was just attached. So that makes it whip back faster. It's enough to overcome gravity even. It'd have to be. And so it whips it back, and then it hits and kind of slides up a little bit. And then then once it stops moving, now gravity's taking over again, and it's slowly pulling it away, creating a bigger magnetic field, and it hits it and whips it back up. So
in my big coffin example, you pull it away, like you tilt it away, leaving a little gap at the top of that small face. Let go, it would be attracted back and kind of scoot up. Pull it down again, let go, it would slap it back, and the coffin would start to just like scoot its way up.
Yeah, but I think rather than you pulling it away, it's the other way. You're holding it up, flush against the surface, and then you let go, and gravity pulls it down a little bit, creates a little bit of a wedge, and then it snaps back up. So maybe this is a bad thought process, because I think in theory it would just constantly move up.
I was just going to say, we basically have a perpetual motion machine.
Yeah. Okay.
Why do we even need elevators? Just attach coffins to the sides of buildings.
Yeah, exactly. So, I'm thinking less likely that that's it.
Yeah.
The whole thing with all of everything that we just said is none of that takes into account that stuff is spinning.
Right.
Because if we add in spinning somehow, that's going to be some sort of energy input that could give it the energy to move up, or that is giving it the energy to move up.
I'm still wondering if no spinning, but just that, going back to that picture from Wikipedia of the sheet moving to the right, if we put that sheet vertical, like it was a wall, and had the magnet be weighted on its back, so it's feeling gravity trying to pull it down.
Okay.
And slid the wall to the right, the vertical wall now, would the magnet climb up the wall?
Right. That's what I was kind of like getting at a little bit earlier, is that all the eddy current talk is creating forces in the direction of motion. They have nothing to do with up and down forces.
Right.
So it seems like, in that situation you just described, no, it would just pull it with it. The only thing I could see that in terms of eddy currents that could help pull it up is when it gets pulled away, your Lenz's law is going to try and add back more. Right.
Yeah, like the screwdriver and the drill part, like imagine putting a ruler to prevent the magnet from moving with the sheet as it moves to the right. And then if what I'm saying is correct, then it should climb up the wall. As the walls move to the right, we hold the magnet in place with the ruler, just like the screwdriver one on the drill.
Right.
Then the magnet should climb up the wall as that vertical sheet moves to the right.
Right, yeah.
So I was trying to tease out spinning from the motion. Yeah. Is what I'm describing incorrect? And then you're going to say it's spinning. Does that throw in a different type of current that then does cause it to rise up, whereas mine wouldn't? I don't know.
No, I think the situation you just described where you're holding it from moving with the ruler, my gut says that would move up the wall.
Right.
Another way to think about it is just make the radius of the ruler really big.
The screwdriver. Yeah.
Yeah, screwdriver.
Exactly.
But my thought though is that the eddy currents that are produced by the side to side motion of the sheet is not the thing that's moving it up, or maybe it has some other effect. There's another step removed that we haven't seen yet, but those two magnetic fields that get generated aren't helping push it up. It'd only be the gravity one pulling it away from the wall. So, why the sheet moving, how that does something else to the system that, we I don't think either one of us have seen yet.
Well, I'm going to go with it's that pulling away from the top part, that kind of wedge I keep describing. that's attracting the thing up. It just doesn't feel like it's strong enough. Like I could see it being like a resistive force, but to actually accelerate it upwards, that doesn't seem right.
Yeah, I mean, because it's got to be overcoming gravity and friction. Friction's probably pretty low, but it's still there. Maybe I'm getting really crazy now. Is there any way that the magnets themselves could be spinning? Like along their axis.
Right. I don't know what that would do.
Well, if they were spinning fast, then we would get some sort of like gyroscopic effect, like the bicycle wheel. Not the gyroscopic. Well, yeah, I guess a gyroscopic effect, but like it would want to spin on its own. I don't know how that would affect anything, but no. Okay, I'm going to.
I don't know.
You know who this guy looks like? Steve Molden. If he ever hears this, I hope he doesn't take offense. He kind of looks like Kirk Cameron.
Kind of. Yeah, I can see that.
Kirk Cameron's a handsome man. That's what I meant to say.
He also believes bananas were created to fit in their hands or something.
Yeah. He does believe some of the dumbness. Looking like Kirk Cameron doesn't mean you're as smart as Kirk Cameron. Yeah, there is also the sound. There is some sort of that I feel like it's got to be more of like a sound. Okay, here I don't know if you can hear this or not. It's kind of making a sound. It could just be friction, I guess. Yeah, I mean that was just my neodymium magnet rolling around the screwdriver as I. Okay, all right. Can I ask another? Or can we do another test or another thought?
Yeah.
Oh, I figured it out. It's a Phillips screwdriver. I'm using a flathead.
Right. There it is.
No.
We need Torx. We need to get Torx screwdrivers in here.
Yeah, exactly. So when I'm trying it here, I just have like I said, it's riding around the edge of the magnet. Do you think... Like, okay, imagine you had a really big disc magnet that was now attached to the thing. That's going to pull away from the edge as well. And it is also, if you have like north facing up, let's say, it's going to do the same thing that we've already talked about. Maybe not in as great as magnitude, but it will still create that wedge, and it'll still have, north poles, I guess, or south poles being created on the thing. So wouldn't that go up as well? But I'm not seeing that. But this is also kind of like a fairly small magnet. It's like dime sized. So I don't know if that's too small to see this effect.
Can you attach something to that magnet to make it as long and as weighted, like away from the screwdriver?
I've been looking for something.
Yeah.
I might be able to.
Like a lighter, or like I'm trying to think of what, like an everyday object that's maybe around somewhere. And I guess, and super glue. Or just Scotch tape, and like, I'm seeing like a travel little packet of tissues or something like that.
I think I have some stuff that might work. I just kind of need to Legos it together really quick.
Ooh, Legos would be great.
Yeah, I don't have like I don't know if I'm doing it wrong, but it's moving down.
Okay, so I was going to guess, like, how much weight could this magnet have to carry? Like, obviously, we don't use spinning flagpoles and, like, magnetic floors as elevators to raise weight, right? So there's got to be some sort of weight limit. So is this, in the video, is the magnet in the video, like, just the perfect balance of, like, it's light enough to go up, but strong, like, heavy enough that the torque is pulling it away? Like, obviously, if you stood on that magnet as it spins around the screwdriver, it's not going to carry you up.
Right.
So where's the limit? Like, where's the threshold?
Yeah. And that's what I was trying to create. Apparently, I think I'm in between the two.
Is your setup, does it stick to the screwdriver and stay in place without spinning anything? Or does it slide down? Is it like too heavy?
No, yeah, it sticks,
to even stay in place?
And stays in place.
Okay. But when you spin it, it starts going down.
Yeah. So what I have here is like, I mean, I could describe it to you, but essentially what I did is I have a little metal object that I'm able to attach to the magnet, and I have 3 of them. So what I did is I put one of them on, and if I spin that, I think the magnetic field is too much to get it to really spin. They don't slide. Mm-hmm. So then if I add another one to it, so what I did is I put a magnet in between the two pieces of metal now to firmly attach the second metal object. Now that's enough to make it, I think, go down. So So I would need something in between those two masses potentially, and I don't know if I have that.
Where do you stand on watching the rest of this video?
Yeah, I don't know. I was thinking about that. We could watch it and then just be like, oh, we're done, or we could.
Oh, we were close.
Yeah. Oh, yeah.
Yeah.
Or we could try and think about it and then get back to the next one.
I think I'm at the edge of my thinking abilities on this.
All right, so you do.
Because I've thought about it for a long time, and that's as much as I've got, is what we've talked about.
Do we just want to watch it then?
I think we should.
All right. So I'll meet you back in roughly 5 minutes.
Yeah.
Wait.
Okay.
Sorry. Before we get too much further, go to I think it's like 1:30 or so when he does the ruler.
Okay. Yeah, I just watched that.
Does it roll up the ruler? It does. It rolls up the ruler. Because
what is that? I see it, but what does that mean?
I don't know, but like that, that's another element that it is spinning.
It's twisting.
Yeah, the magnets are spinning on their own axis. Does that have anything to do with it?
I got nothing on that.
Could that help it somehow? So if they're rotating, I'm just going to throw out an assumption. Maybe the spinning screwdriver somehow creates some forces that cause the magnets to spin themselves. Mm-hmm. So now if they are spinning, that could create some other eddy currents maybe. I don't know how that then goes back to if they were spinning, it's still spinning kind of in the same direction of motion. I thought maybe we would like add another direction of motion that would like, aha. But no, okay. All right. Well, I don't know. Okay. Should we just watch?
Yeah.
Oh, he does talk about the sound of it.
Uh-huh. That's what I just heard. So you were right. It's all about the spinning. But we were both wrong in that we thought it was very magnetic in origin. And I'm not positive I understand it yet.
I can follow their argument, I think. Mm-hmm. So
oh, we should explain what the argument is.
So for people.
So spoilers if you haven't watched the rest of the video.
Yeah.
This is what they said it
and
is.
If you want to figure it out on your own, pause. You can come back and to us or watch the video, either one. But so they're saying what happens is there is like a stick and slide, or they're calling it stick and slip motion, but it's not up and down like we were talking about. It's left and right. So it wants to, the center of the circle of the magnets is what's stuck, but then as it rotates, it kind of pivots to the edge of the magnet, the contact point. And then because gravity is pulling it down, we create that kind of wedge that Derek was talking about a little bit.
Oh, you just said the part that I was missing. Okay. Now I think I'm on board.
Yeah, and so because there's that little wedge sort of shape, the real contact point is just the bottom part of that off-center line. And I don't know, this is the part I'm not quite sure about, but now it's going to spin around that single kind of contact point. And if you imagine drawing a circle and putting your finger not at the bottom part, but some point on the left, and then spinning it around so your finger is at the bottom. Now the circle is higher than where it started, and so it kind of diagonally travels up it in that case.
So I think the way what you just said made sense. Imagine like a ketchup bottle or a Coke bottle or something cylindrical sitting on a table, which is the magnets attached to the screwdriver, and then I'm taking my water bottle and doing this. Tilt it to one side and kind of balance on like the edge. There's like one point of contact, right? Mm-hmm. So this is the first thing to do. Well, man, yeah. Tilt it on an edge. And then I think what's happening is, now I don't get it anymore. Why does it pivot around that one point and rotate upwards. So the part of the video that I was like, I don't see why that happens is 550.
Right, well, so I understand everything except exactly why it rotates around that point.
Exactly. That's exactly where I'm stuck, is why does it rotate about that point upwards? And he shows it at 550 slow motion with his finger pointing to it.
Right. Like, so, I mean, I can follow his idea. So yeah, like if you go to exactly what Derek said and put your cup on the table in front of you and make gravity down towards your body and upwards away from your body. So then if you, or maybe it's better if you put your finger under the can. Okay. So right now it's under the can and it's the center of the can is over your finger. Move the finger to one side of the can and then pull down on the glass a little bit towards, gravity downwards towards your body. Now there's only like one point that's in contact with your finger anymore, and rotate the glass around that point until that point is at the bottom now. Then put the glass back up if you notice your finger's in the center again. So you can just repeat that. Move your finger to the side, pull down again. You have that one point in contact, rotate up till your finger is at the bottom of the cup again, or the can, and just repeat. And if you keep doing that, you'll notice that the glass is walking upwards. It's walking away from you slightly. So right. I follow all of that, but why that rotation happens?
Right, exactly.
I'm not sure. Other than it describes it.
And I think it goes back to the first thing they were talking about, which is the slip stick, where the slipping is more on the top. It slips more because there's less of a contact force at the top of the cylinder.
Okay, yeah. So there's another... I don't think they really said that explicitly.
They didn't say that, but I think that's what it is.
Yeah, I can see that because, when it wants to slide, or maybe they did say this, but it just didn't come off very clear. Right. But yeah, when it wants to slide back to center, there's more force at the bottom of it than at the top, which will cause it to rotate as it slides back.
The top is more free to move, so it's going to rotate more than the bottom, which is kind of stuck in place more. It still slides, Yeah, maybe it doesn't. I don't know, but it's the top is free to rotate more than the bottom is. So we were both kind of right. I was right with my little wedge situation, although it wasn't exactly explained. That didn't exactly explain it. But you were right in that we should have been paying attention to it twisting. But neither of us were right because we both thought it was some sort of eddy.
Yeah, I definitely thought it was somehow related to, like, this really doesn't have a whole lot to do with the fact that it's a magnet. Like, other than that's the thing, like... It
has to hold it up. Yeah.
Keeping the...
And my idea with the sheet, the vertical sheet...
Wouldn't work.
According to this, it would not work. Yeah.
So, yeah, that's the test for this, right? Is to... Well, wait. Oh, yeah, because the reason it wouldn't work is you could still get that spinning sort of thing, but you're not getting the initial slip and stick phenomenon. Like in the example, like your finger isn't going to move off center ever.
Right. Why does it stick and slip? Oh, it's because the magnet. Imagine like you just put the left edge of the cylinder in contact with the screwdriver, the left edge of the magnet face. And let go, it would try and like slip into being centered on the screwdriver. So that's the like, it starts to do that and then it slips back, it like snaps back into the centered.
Yeah, like the center part wants to stick. So you get like a pivot around that slightly, which then puts it off center, and then you just get this slick little motion that happens.
Right.
Man, that's wow.
I was excited when he started talking about the sound. I was like, oh no, we were onto something and didn't pay close enough attention, or we were right. It is going to snap back and forth. And then he said stick slip, and I was like, oh, that's exactly what it was, is the kinetic versus static friction, but not in the way we were thinking.
Right. I want to like find out ways to test this. So definitely the sheet, I think, would test it. I thought I had a really thin screwdriver, like a one with a very small radius, and I was thinking I should be able to use my one magnet potentially with a small enough radius to kind of get this effect to happen, but I could not find a really thin one. Apparently I don't have that. But right, wouldn't that make sense? I can't do it. So I don't know what the diameter of this is. Maybe it's like 5 millimeters of the screwdriver that I have now. So I was thinking maybe if I could get one that had like a diameter of 1 millimeter or less, that I could get this rotation thing to happen.
I feel like the diameter of the screwdriver doesn't affect things.
Well, but what if it's an infinitely large diameter?
As long as it's not infinite, I think it would still work because it's always based on one line of contact, no matter the radius.
Yeah. Okay. I could see that. But then why did... Okay.
Like, I actually think it would work instead of a cylindrical, like, screwdriver shape. It would work with a hex shape.
Oh, I could see.
Or like any. I mean, if it's a square, like a I don't know what those are called, square prism, it would do this on the edges, but it might get stuck in like one of the faces, right. Or like a triangular prism. But if you had a lot of like edges, like I imagine a hexagon, it could do this.
But okay, why?
As long as it goes from one edge to another edge.
So. I'm trying to figure out why mine goes down. Is it still mass related, or
yours might just be too heavy?
Yeah, the other thing that's happening is mine is not cylindrically symmetric. So the center of mass, I think, is probably slightly below the little metal bits that I was adding. Is probably slightly below the center of the axis of rotation. So it might be that it's weighted to go down one way than preferentially, and then maybe that's why it goes down.
Yeah. Well, cool.
Listen, yeah, I mean, I like his ending little speech, or he kind of gives it in the middle too, but like, it's kind of interesting how there's these sort of like simple little things that like, like no physicist is going to get a PhD for thinking about, but that are like not easy to solve. Like it's not straightforward exactly what was happening here.
Exactly. Yep. No PhDs, but hundreds of thousands of YouTube views.
Yeah. So if you have any other, if you think of anything, audience, that's interesting like this, feel free to send it in to us. I'd like to play around with it.
For sure. Yep. Well, that was cool. I don't know if I'm sad we didn't get it. I was at the end of my abilities and we were going down the wrong track with electromagnetic stuff.
Yeah. I
kind of, but yeah.
I would have sworn that would have been it, but yeah, I mean, I guess not. I wonder, there is some effect here. Like, I still think everything that we said happens. Like, I don't think we said anything wrong. It's just, it's not.
It wouldn't be enough. Like I was saying, like, I couldn't believe that force would be enough to pull it up.
Right.
Yeah. Well, cool. All right.
I'm still stuck thinking about like, how can we test this?
Push it further.
Yeah. Cool. Well, thanks for listening, I guess. And we'll catch you next time.
Yep.